Hello, everyone. In this lecture, we're going to talk about the project management. So I think you are familiar with the project. We always want to do some of the project. For example, we are taking some classes. So also, we have the class project. So in this part, we're going to talk about how to schedule different projects. In order to complete a project, we need to complete some activities. But how to figure out activities? So we should use the work breakdown structure method. We use this method. We want to break down the entire project into different the smart activities. And then we want to go further to break down the small activities into the smaller activities. So this we call this method the work breakdown structure method. And then we identify activities based on different uh, prescriptions or specifications. We figure out the different events as well. For each activity, we need to identify time, cost, resource requirements. And then we also need to know the relationship between activities. Okay, and then we can make a schedules for project specifically for activities. And then we're gonna use the two methods to handle project scheduling. So there are two methods available. The first one is called the PERT, Program Evaluation and a Review Technique. The second one is called the Critical Path Method. We use these two methods to figure out the critical activities. Why we wanted to find out all the critical activities because all activities are critical. We have to figure them out, and then we want to know whether or not we can complete the entire project on time, because critical activities can affect the completion of the entire project. We don't want to delay uh, the completion of the entire project. This is why we have to find out all the critical activities. We use support the method to calculate activity times, and then we can to calculate estimated completion time for the entire project. And also we needed to use the CPM to figure out all the critical activities. We use them together, so we call like uh, the PERT or CPM. I put them together. We need to follow some steps for PERT and the CPM. There are 6 steps here or there. The one, define the project and all of significant activities or tasks. Number two, develop the relationships among the activities. Decide which activities must precede others. Three, draw the network connecting all of the activities. Four, assign a time and a work cost estimate to each activity. Five, compute the longest time path through the network. This is called the critical path. So you should know the critical path is the longest time path through the network. And six, use the network to help plan, schedule, monitor, and control the project. Here, basically, we want to calculate the probability that the entire project will be completed on time, or it's not on time. We want to know the probability, so we cannot complete the entire project on time. So basically, we want to know the probability. Actually, we calculate this kind of productivity in chapter 2 when we talk about the probability. So we're going to use something we learned from chapter 2 to solve some problems in this chapter, project management. Critical path is very important. That's why we needed to find out all the critical activities on the critical path, because we cannot delay the critical path, the critical activities. Otherwise, you're going to have some the problem regarding completing the entire project. Basically, we talk about the delay of the entire project. Let's look at example. I want to use this example, the General Foundry example, to show you how to schedule products, how to calculate estimated activities times as well. So let's look at this example. A General Foundry incorporation has long been trying to avoid the expense of installing air pollution control equipment. The local environmental protection group has recently given the foundry 16 weeks to install a compressed air filter system as the main smokestack. General Foundry was warned that it will be forced to close unless the device is installed in the allotted period. They want to make sure that the installation of the filtering system progresses smoothly and on time. And now you can look at this table. This table shows activities and immediate predecessors. So we can see there are some activities from from A to the H, and then we have some descriptions. Basically, based on descriptions, we need to figure out the relationships among activities, and are we want to know which activities are immediate predecessors. For example, we look at A and B. A uh, build internal components. So we can see A has no immediate predecessors. What does it mean by immediate predecessors? It means uh, after you finish this activity and then you're going to start A immediately. So in other words, this is another activity before A that will be immediate predecessor of A. But from this table, we can see A has no immediate predecessors. In other words, A must be a start node. So we're going to start the entire project from activity A. And it's the same thing for the B. B is to modify roof and floor. The same thing here, the B has no immediate predecessors. So also we can see that B is also a start point. So A and B are both start points or start nodes. We keep going, look at the C and D. C is to construct the collection stack. But you can see C has an immediate predecessor, A, and D, the poured concrete and installed frame, D has a immediate predecessor, B. So in other words, in order to do C and D, you have to start uh, A and B. But also you have to finish A and finish B, and then you can start C and D. Right? So this is about immediate predecessor. Basically, we want to show the relationships among activities. Let's look at two more activities. Let's look at E. E is to build a high temperature burner. So you can see E has an immediate predecessor, okay, C. In other words, we have to complete activity C and then we can start activity E. And similarly for F, we have to complete activity C and then we can start activity F. Right? But for G, uh, is a little bit different for G. So you have to complete activity D and activity E, and then you can start activity G. So you should be careful here. This relationship is very important. If you cannot figure out the right relationship between activities, you may have the problem to draw the network, and you will have the problem figuring out the critical activities, even critical path. And so this is very important to know immediate predecessors for each activities. The same thing H is to inspect and test. H has two immediate predecessors, F and G. In other words, we have to complete activities F and G, and then we can start activity H. We just talk about the table, talk about description of activities. But right now, we want to use another technique to show the relationships among activities. We call this network. In chapter 9, when we talk about transportation, and assignment problems, we introduce a network. When it comes to the network, there are two terms we need to know, nodes and arcs. The same thing here, we're going to use nodes and arcs. So we needed to know the two common techniques for drawing the port networks. Activity on the node, AON. The nodes represent activities. Activities on the arc, AOA. Arcs represent the activities. The AON approach is easier and more commonly found in software packages. So we are going to focus on the first technique, activity on the node. We want to talk about the second one. Okay? But also you should know uh, something regarding the network. One node represents the start of the project. We call start node. Also, there's one node for end of the project. We call the finish node. So you need to show these two nodes clearly on the network. Later on, I'm going to show you. And also, you need to use arcs to show the relationship between the two activities. But you should know you have to use arrow to show the relationship. Right? Let's look at this picture. Right? This network for this example. You can see we put a start node and a finish node. Right? So start nodes uh, means we're going to start a project. The finish nodes mean we're going to finish the entire project. So for network, you have to draw a start node and a finish node. And then you're going to put activity node, right? For example, A, this activity A, and we write down description for A and the C. Right? But you may notice the arc, right? This is the arrow that shows the relationship because we already know A and B have no immediate predecessors. So that's why we just put a start node. But for C, C has an immediate predecessor, which is A. So that's why you can see we use arrow, use an arc, arrow to show this relationship between A and C. The same thing for B and D, right? Because the B is an immediate predecessor for activity D. So that's why we do it this way. We use the arrow to show the relationship. Uh, because we want to find out the critical activities. So we needed to figure out activity times, and then we can figure out the longest time that pass throughout the network. So this is why in this part, we're going to know how to calculate activity times. But you should know activity times could be the random. Sometimes if you have enough information, basically you can figure out certain activity times. There's no problem for that, but in most cases, we cannot figure out certain activity times. So we have to look at random activity times. So in this part, we're going to talk about how to calculate activity times and how to figure out the critical path as well. Uh, in the meanwhile, we're going to talk about how to calculate the completion time of the entire project as well. And you should know the two different processes here. The first one is the forward process. The second is backward process. We're going to use these two different processes to figure out critical activities in the network. Also, you should know something else here. We use the port to figure out activity times. Basically, we talk about the three estimate of uh, time for each activity. And then you're going to use the two formulas to calculate expected uh, activity times and also variance for activity times. Right here. So you can see there are three time estimates in the part. The first one is optimistic time. Uh, a time an activity will take. If everything goes as well as possible, there should be only a small probability of this occurring. the pessimistic time. Time and activity would take assuming very unfavorable conditions. There should also be only a small probability that the activity will really take this long. The last one is most likely time, and the most realistic time estimate to complete the activity. I think you are familiar with these terms because when we talk about decision making uh, under uncertainty, we talk about some of the method, optimistic method, the pessimistic method, and the equally likely method. They are very similar here. And then you should know the PERT assume the time estimate follow a better probability distribution. Uh, and then after you know three estimates of activity times, then you can calculate the expected activity time for each activity. So you can use this formula. T equals A plus 4 times M plus B divided by 6. And then you can calculate the variance of activity completion time. Variance equals B minus A divided by 6, and then square. So you should be careful here. You should calculate B minus A divided by 6 first, and then square. You should pay more attention to the parentheses right there. Let's go back to our example. So we're going to use uh, the parameters in this example. Basically, we talk about the data to calculate expected time and the variance for each activity. I just give you an example. Let's look at activity A. So we know optimistic time is 1, the most likely 2, pessimistic time is 3, and then we follow this formula, and then you can calculate the expected time for activity A. So we plug all numbers into this formula. A equals 1, 4 times M to the 4 times 2, and the plus B is 3, and divided by 6. So this is the 2. And also you can calculate the variance of activity completion time. So the B is given the 3, and A is given is 1. So 3 minus 1, this is the 2. This is the 2. And 2 divided, this 2 divided by 6 and then squared, right? Like this. So you should be careful with the variance formula. And then you can keep going. You can calculate expected times and the variances for all activities. After calculating as expected activity times, so we can put them into the network like this. So we should look at this network. This is the start node, and we have activity node. There's a activity node. So you can see there's this activity name, along with activity time. This is expected activity time because activity times are random. That's why we looked at three estimate of activity times. Using the formulas, we figured out activity time. This is the expected activity time. Right? And then we put them into uh, node, into the nodes, and then we can see the network should like this, should be like this, right? And then you can keep going because our goal is to find the critical path. But how to find the critical path? So we wanted to use expected activity times and to uh, figure out uh, early earliest finish time, earliest start time, latest start time, latest finish time, and then we can figure out the critical activities. So right now we're going to know how to figure out critical activities. Before finding out the critical activities, we need to introduce some of the terms here because they are very useful to figure out the activities that are critical. Let's look at the first one. Earliest start time, short for ES. The earliest time an activity can begin without a violation of immediate predecessor requirements. So you should know this is ES. When you calculate ES, and then EF, EF earliest finish time, the earliest time at which an activity can end. 3. Latest start time, short for LS, the latest time an activity can begin without delaying the entire project. Number 4. The latest finish time, short for LF, the latest time an activity can end without delaying the entire project. We needed to calculate all 4 times, ES, EF, LS, LF, and then we can calculate the select time for each activity. If the select time equals 0, that activity is critical. Otherwise, that activity is not critical. So this is a general idea for finding the critical path. Right? Now let's look at this node. So we want to add more element into this node, into the activity node. You can see here. So this is the activity name, and here is the activity time. This is the expected activity time, and then you can see here this is ES, EF, LS, LF. So we need to add ES, EF, LS, LF into the activity node. And also we needed to follow some more formulas to calculate EF, and later on we talk about LF as well. Okay. For example here, so we talk about earliest finish time. So earliest start time plus expected activity time. ES plus T equals EF. So this is the formula. Earliest start time, but we needed to determine the next earliest start time, ES, for next activity. We use this formula. Largest of the earliest finish times of immediate predecessors. The ES equals largest EF of immediate predecessors. This rule or this formula is very, very important because later on we talk about the forward the path. We're gonna use the forward path to calculate ES, EF. So we're gonna follow this rule. Okay, let's look at some examples. You may see here, this is the start node, this is start node, and activity nodes. Okay, 2 activities, A and B, and we already knew A's activity time is 2. Yes, because A has no immediate predecessors, that's why early start time for A is 0. And 0 plus 2 equals 2. So EF equals 2. And for the B has no immediate predecessors. That's why ES for B is 0. And 0 plus 3, 0 plus 3 equals 3. So EF for B is 3. So this is the way we calculate EF based on the value of ES and the value of expected activity times. Okay. Next, we can figure out all the ES, EF for all activities right now. So we just do the calculation here. So follow me go through this process. Okay, notice this is the ES for A is 0 and activity time for A is 2. So 0 plus 2 equals 2. Later on, I just say activity times. I don't say expected activity times, but you should know when I refer to activity times, I mean they are the expected activity times. And 0 plus 2 is 2. And the C has only one immediate predecessor, so we can see here. So this largest, the EF for the C, so just be 2, the 2. So this is the ES for C equals EF of A, so this is the 2. Just copy 2. 2 plus 2 equals 4. Okay, do that this way. And we go to the B. B has no immediate predecessors, so this is why the ES for B is 0. and then 0, and then the activity time for B is 3, is 0 plus 3 equals 3. EF for B is 3. And the D has only one immediate predecessor, so that's why the ES for D must be equal to the EF of B, the 3, because we should follow this rule. We should follow this rule. Earliest start time equals largest of the earliest finish times of immediate predecessors. This is the why. But for C and D, both have only one immediate predecessors. This is why we just choose 2, just use 2, or for A and B is 3, and then we set ES for C to 2 because of the EF of A equals 2, right? So the same thing for the D. Now we keep going, and then we should look at activity F and E. F has only one immediate predecessor, C. That's why, so EF for F must be equal to EF of C. So 4, 4. And 4 plus 3 equals 7. EF of F equals 7. And the same thing, E has only one immediate predecessor, C. So we just make them equal, right? Make them equal. And 4 plus 4 equals 8. So the EF for E equals 8. Equals 8. Right? Now we move to the G. G is a little bit different. Okay? Why? Because G has two immediate predecessors, D and E. Okay? So this time, when we're trying to figure out the ES for G, we should use the largest of EFs of G's immediate predecessors. Now, we know E and D are immediate predecessors to the G, so we will look at their EFs. For E, its EF is 8. For D, its EF is 7. We should choose the maximum, the largest. Largest is the 8. So now this is the 8. 8 plus 5, so this is 13. But here I want to explain why we needed to choose the maximum or the largest EFs among immediate predecessors. Because we needed to follow the rule, a relationship rule. Right? What does it mean by the relationship rule? For example, right? If we don't choose 8, we choose 7, we want to see what would happen. If we choose 7, so we put 7 here, 7 here. So if we put 7 here, so we can see here the G started after D is completed. But there's a problem. But there's a possibility the activity E is not completed yet because the EF earliest finish time for E is 8. So this is impossible. Why? Because E is in is the immediate predecessor for G. In other words, so we have to complete activity E and then we can start activity G. But right now, if we set ES for G to 7, G is already started, but E is not completed yet. So this is impossible. Okay, this violates the relationship rule because we have to complete E and then we can start G. This kind of a relationship because E is the immediate predecessor of G. So this is very important. You should understand this. And then you can see we got 8. 8 plus 5, 13. So the EF for G is 13. The same thing for H. H has two immediate predecessors, F and G. We should choose the largest EF, right, among F and G. 13, 7, 13. So 13 plus 2, the 15. And finished. Right? So you can see this is we call this process the forward the process. This is the forward process. Forward process. Right? Use forward process also we can figure out the completion time of the entire project is this one, 15 weeks. So this project can be completed in 15 weeks. So this is the completion time for the entire project. Why? Because once the activity H is done, the entire project is done. So this is why the 15 weeks is completion time for the entire project. So you should know how to figure out the completion time for the entire project. You can see this is a forward pass process. Also, we call this forward pass as well. So we can use the forward pass to figure out the completion time of the entire project. And also, we can calculate the ES and the EF for each activity. But we want to find the critical path. Okay, this is not enough. We just finished the first part. We just use the forward path process to figure out completion time of the entire project and ES, EF for each activity. But also we should keep going with the backward path or backward process to figure out LS and LF for each activity. And then we can calculate the select time for each activity. Then we can know which activity is critical. Right, so let's keep going. Before calculating LS and LF, we need to introduce some terms, introduce some formulas as well. So we call this a process the backward the pass backward pass. We needed to calculate the latest time and the latest start time. We use latest finish time minus expected activity time. We use this formula. LS equals LF minus T. So we call it backward. So we're going to start from the last activity H. Latest finish time. So we use this rule. I call this rule. So the smallest of latest start times for following activities. Uh, Previously, when we try to use the forward pass, we wanted to figure out the largest of EFs for all immediate predecessors. But this time, we should look at the followers. So this time is a little bit different. So we should choose the smallest LS of following activities. For example, for activity H, because I just mentioned H is the last activity, so we use the backward path. We should start from the activity H. So we need to calculate LS equals LF equals uh, LS equals LF minus T. Here, I want to explain why we set EF for activity H to the 15 here. Because H is the last activity. Once H is done, the entire project is done. So this is why the EF for H must be equal to LF for H. the latest finish time, earliest finish time, they must be equal. Now let's look at the backward, the path, the process. So we're going to start from negativity h. We know EF, LF for h are equal, so they are uh, both 15. So the 15, 15. 15 minus 2 equals 13. That's LS for h. Right? Now we go to the F because F has only one follower, so we should choose the smallest of LS. The LS 13, so that's 13. 13 minus 3 is 10. So LS for F equals 10. And look at the G. G has only one follower, H. So we should choose the smallest of LS, right? But we know there's only one follower. That's why we should set LF for G to 13. They must be equal. 13 minus 5 is 8. So it's 8. LS for G is 8. Okay, now we move to the E. E has only one follower, G. That's why they must be equal. So LF for G must be equal to LS for G. So 8. 8 minus 4, right, equals 4. So the LS for E is 4. 4. And then we go to the D. D has only one follower, G. So this 8, that must be equal. 8, 8. And minus 4, okay, 4. So LS for D is 4. Is 4. And B has only one follower. So this is the 4. This is the 4. Right? This LS for D is 4, and we should make them equal. So LF for B must be equal to 4. So 4. 4 minus 3 equals 1. Right? Like this. Now we go to the C, but the C is a little bit different. Why? Let's look at the C. C has two followers, F and E. We should choose the smallest LS among followers. Okay, basically we talk about immediate followers. So we know the LS for F is 10, LS for E is 4. We should choose the smallest. Which one is smallest? Is 4. Right? Why? The same reason as I explained for the forward pass. The relationship rule. Right? For example here, if you pick the highest or the largest 10, what would happen? So in other words, this is the 10, this is the 4. If we put a 10 for C, what would happen? You can see here, the C is not done, but the E has started. This is impossible because we have to complete activity C and then we can start activity E. That's why we have choose the minimum of ELS among immediate followers. So this is 4, 10, 4. The 4 minus 2, 2. A has only one follower, right? That's 2, 2. 2 minus 2, 0. And like this. We call this backward the path or backward process. But right now, we're going to reach the concept of slack time. We want to calculate the slack, and then we can figure out the critical activities. If the slack time is 0, that activity is critical. So this is the general idea. So how to calculate slack when you use this formula? You can use LS minus ES or LF minus EF, right? Like this. Then you can figure out the critical activities. So we can see what activities are critical activities. Absolutely, you can use this table to do calculations. You can figure out which activities are critical. because if the select time is 0, okay, that activity must be critical. You can do it this way, but I prefer the network. Right? A network uh, is very easy to use and is very easy to see which activities are critical. For example, here we talk about select time. We use LF minus EF or LS minus EF. Let's look at A because 0 minus 0, 0, 2 minus 2, 0. So select is 0, so A is critical. The C, same thing, the 2 minus 2, 4 minus 4, 0, 0. Okay, so this is critical. But let's look at F, the 10 minus 4, 3, and 13 minus 7, 6. Right? So slack is not equal to 0. So this is not a critical. The same thing for E, for H, for Z. You can see if you use the network, it's very easy to figure out which activities are critical. So you can see the A, C, E, G, H, they are all critical activities. Now we're going to talk about how to calculate the probability of completing the entire project. Basically, we want to complete the entire project on time, but sometimes because of random activity times, so we cannot complete the entire project on time. So we want to know the probability that we can complete the entire project on time. So that's why this part we're going to calculate the probability for completing the entire project. But based on uh, forward path and backward path, we already figure out the completion time for the entire project. We call that the expected project completion time. We already knew this number, the 15 weeks, by using forward path process. But right now, we want to calculate the variance for the entire project. So how do you calculate the variance? You should remember uh, this part. In order to calculate the variance of the project completion times, you should look at the variance of critical path activities. In other words, you should look at the variance of critical activities. So this is a very important part. We don't need to look at all the activities in a project. We just need to look at the critical activities. So this is a very important point. Okay? Don't be confused. Very important. And then how to do calculations? Okay, you can see here. You just use the variance of critical activities, okay, and them up, and then you can get the project variance. And then you can calculate the project variance for this example. So we already knew the variances for all the activities, right there. We calculated using that formula, and then we can add them up. Right, we got the 3.111. This is the project variance. Further, we can calculate project standard deviation. We can take a square root, and then we can calculate project standard deviation. Standard deviation is 1.76 weeks. So also we assume activity times are independent, and the total project completion time is normal distribution. Right? This is the Bell-shape. We're going to use normal distribution to calculate the probability. Right? Like this. We are familiar with this, the Bell-shape in chapter 2. We already talked about it. We knew expected the completion time and the standard deviation. We can uh, plug them into the formula. We want to calculate the z-score with z-value. We want to know the probability that the entire project will complete in 16 weeks. We want to calculate this probability. So 16 weeks minus 15 weeks divided by 1.76. We got a 0.57. This is the z-score with z-value. You can use the table or you can use the Excel. Like what we did before, we can use the Excel and then we can figure out the probability. Now you can see the probability is 0.716. This is the probability, right? And you can look at this graph, look at this curve here. Right? So we want to calculate this probability shaded area, and then you can use the Excel, we will use the table, you can figure out the probability, right? Because you know expected completion time and the standard deviation as well, and then you can calculate the probability. And basically, we want to know the area, so you know the 71.6%. And then you can get some insights and also make some decisions or conclusions. For example, here, so based on the PERT and CPM method, you can know expected completion time for the entire project is 15 weeks, and also you know there's a 71.6% probability that the equipment will be in place within the 16-week deadlines. And also you find out the critical activities A, C, E, G, H because they are critical, so we cannot delay them. If we delay them, we would delay the entire project. And also you should know there are three activities. The B, D, F, they are not critical, right? Because they have the select time. And then based on the forward process, the backward process, you can uh, develop a detailed schedule. Uh, so this we call the project scheduling.